Hello and welcome to Database Management Systems. I'm Jovita Christie, and in this video, I'm going to explain to you conflict and view serializability in transaction management. So let's begin. First, we are going to answer the question of what is serializability. And serializability is nothing but the ability to make a schedule a serial schedule. And I've discussed serial schedules in my previous video. There are two types of serializabilities. The first type is the conflict serializability, and the second is the view serializability. And first, let's take a look at conflict serializability. Now consider that you have two transactions, I and J, and there is one data item Q. So these are the rules for conflict serializability. The first rule is that if I is reading Q and J is also reading Q, then the order of those two operations does not matter. And this is obviously because they are only reading the values. They are not changing the value of Q. So it shouldn't matter whether the value of Q is read by I or J first. So that's why the order doesn't matter if both the transactions are trying to read the same data item. The second rule is if I is trying to read Q and J is trying to write Q, then the order matters. Because in this case, if the transaction I is first reading the data item Q and then the data item Q is being written by J, then the transaction I will not get the value written by J. But if transaction I is reading after J finishes writing the data item Q, then the transaction I will get the new value of Q, which is updated by J. So in this case, the order of these read and write operations does matter. The second case is, of course, where I is trying to write Q and J is trying to read Q. So in this case also, as we know, the order does matter. And once again, order matters because the data item is the same and the operations being performed are read and write operations. And fourth rule obviously is write, where I is writing Q and J is also trying to write Q. And in this case also, obviously the order matters because there are two operations being performed on the same data item. So we need to make sure that the operations are being performed in a certain order. If that order is changed, then the value of Q will get changed. So now once we have understood all the rules, now let's go and take a look at this schedule. Now I've already explained what schedules are in my previous video, and so you do not need to understand. If you don't understand that, then you can watch that video. This is a schedule of two transactions, T1 and T2, and all they are performing are certain read and write operations. So you can see here that they are performing some read and write operations, and I have created a sort of a timetable of which transaction gets to go first. Now, using these four rules that we have, I'm going to try to check if this schedule is serializable or not, if it is conflict serializable or not. That is our topic, conflict serializability. So let us see. First of all, I'm going to try to compare this read A operation with the operation which is right after it. Now, if you check, this is the read A operation, and right after that operation, there is the write A operation. Now, both operations belong to the same transaction. So obviously, there is nothing you can do over there. But check the write A operation and the read A operation. Now, both are belonging to different transactions and applied to the same data item. Now, in this case, one of the rules can be applied, which is given here. So you consider that T1 is transaction I and T2 is transaction J. and they are both working on the same data item. So you can apply one of these rules. Now you can see that first transaction is doing write A and the second one is doing read A. So it's a read-write type of operation, which means you could either apply the second rule or the third rule, depending on which transaction you selected as I and which one you selected as J. But in either case, the order matters, which means I cannot shift this anywhere, means I cannot put write A down and take read A up. That is not possible. So next thing that I can do is try to compare read A with the next operation. Now read A, next operation after read A is write A. And both are belonging to the same transaction, which means none of these rules can apply. So I'm going to now compare my write A operation with the next operation, which is read B. Now, in this case, you should notice that here write A operation has a variable A and read B has a variable B. So in this case, both are different. And hence, you cannot apply any of the rules that are present here because both the transactions are working on different variables. But this also means that their order doesn't matter at all because one transaction is trying to modify some other variable and another transaction is trying to read some other variable. So what happens in T2 does not actually affect T1, which means I can change their order. So that means I can bring write A down and read B up. So let's do that. Okay, now I'm going to compare read B with read A, which is also, as you can see, is present here. Now, when I compare read B with read A, once again, they are working on two different variables or data items, and that's why I can also swap the two. I don't need to keep the same order. So I can bring read A down and read B up. Okay, and that is done. Now consider this part, which is write B. If you compare write B with write A here, then obviously both are again working on different data items. So this also can be shifted. And then once again, write B and read A, both are also different data items. We can shift that too. And that's it. What you see here now is a conflict serializable schedule. So this schedule that we began with, which was having everything happening differently, where both transactions were happening together, I was able to convert that schedule into a serial schedule where one transaction finishes and only then another transaction starts. So all this was done by applying these 4 rules that are present here. And that's why we can say that the schedule that we began with was a conflict serializable schedule because we were able to convert it into a serial schedule. Now let's take a look at a schedule which is not conflict serializable. In this schedule, you can see that there are 2 transactions, T1 and T2, and both of them are working on the same type of data item, which is A. And in this case, if I try to check all the rules, so first I'm going to compare read A with write A. So obviously I cannot interchange those two because I would be applying either rule 2 or rule 3, depending on which transaction I picked as my I transaction and J transaction. So due to that, I cannot interchange these two because order matters. And if we consider write A and write A present over here, 2 different rules, then I would be applying the rule number 4 about 2 write operations being done by 2 different transactions on the same data item. So in this case too, I cannot interchange them. And that's why I'm unable to interchange any operation with any operation. And so this is forming a non-conflict serializable schedule, as you can see, because I'm not able to convert it into a serial schedule. Now, in this, this is a very simple process of checking if it is a conflict serializable schedule or not. But imagine that you have a huge system, a huge banking system that has several schedules and that has hundreds of transactions running at the same time. And so each schedule is having hundreds of transactions. You cannot apply all the 4 rules and check each and every conflict that is happening. So to avoid that, we have a shortcut which is known as a precedence graph. Now, before we understand what a precedence graph is, I'd like to explain a data structure called graph. It looks something like this. There are vertices. So what you can see here in circles, they are all vertices. And 2 vertices are connected with each other by the means of an edge. So wherever you see a line connecting somewhere, that is an edge. So this is called a graph. Now using this data structure, if you are, of course, programming it, you would want to use a linked list in order to connect all these nodes, or you would be using a 2-dimensional array to connect all these nodes, a matrix which is created. So this is a graph, and using this graph, I can create a precedence graph. So let us see how to do that. Now, again, I want you to consider 2 transactions I and j with data item q, as we did before. And here, I'm going to show you rules about when we can add an edge, a connection between 2 transactions in a precedence graph. So in this case, the first rule is if I executes write q before j executes read q. This is the first rule. The second rule is if I executes write q before j executes write q. And the third rule is if I executes read q before j executes write q. So there are three rules which you need to remember, and they are not very hard to remember. Now let's take an example. So this is the transaction, this is the schedule that we used earlier to check for conflict serializability, and the same schedule I'm going to use again. So there are 2 transactions, T1 and T2. So let's make vertices of those 2. So there are 2 vertices, T1 and T2, because there are 2 transactions. And now we will create an edge between these 2 if one of the 3 rules mentioned over here are satisfied. So in this case, there is an edge from T1 to T2. The reason is there are several operations being done by T1 which are done before T2. For example, read A, write A, both are done before T2 does its own read A and write A. So this satisfies, we can say, rule A and also rule B. Yes, it satisfies rule A and rule B. So that's why these 2 are, that's why we are creating an edge from T1 to T2. Now, once again, for read B and write B, and here also read B and write B, we would have to create an edge because again, T1 is doing all these operations before T2. But in this case, there's no point in creating an edge again because we already have one edge over here. So we are not going to create the same type of edge again, and we will leave it as it is. And you can see that this is the only graph that I can get. I cannot get another edge that goes from T2 to T1 because there are no operations that T2 performs before T1 performs on the same variable. And so when you get a graph of this type that has no cycle within it, then it is known as a conflict serializable schedule, which we saw earlier also by applying those 4 rules. Now let's try to create a precedence graph for a non-conflict serializable schedule, which is right here. Once again, there are 2 transactions, T1 and T2. So we will create 2 vertices. One is for T1, another one is for T2. And as you can see, there are arrows going from T1 to T2 as well as T2 to T1. And because the reason for this is when you check this, you can see T1 is doing read A before T2 does write A. So this is the rule number C that is being applied. So we can create an edge from T1 to T2. Another thing that's happening is T2 is also doing read write A before T1 is doing write A. So in this case, our rule B is applied, and that's why we can create an edge from T2 to T1. And you can see there's a cycle formed here, which starts from T1, goes to T2, and then back to T1. So this is a cycle. And that is why whenever there is a cycle in the precedence graph, we say that this schedule is non-conflict serializable schedule, as we also saw earlier by applying those 4 rules. Now let's go to the next type of serializability, which is known as view serializability. Here also, as usual, there are some rules. The first rule is that for the view serializability, the read operations, the first read operations should be done by the same transaction in the schedule. The second rule is that the order of read and write should not change for the same data item. And the third rule is that the final write operation done to any data item must be done by the same transaction. And I'll tell you what this means by an example. Let's create a serial schedule for this, which will look like this. You can see here T1 is finishing all its operations, and then T2 begins, and then T3 begins. So we are going to compare these two, and if they satisfy all the 3 rules that are mentioned up there, then the schedule that we are talking about is a view serializable schedule. So let us see. First, we are starting with the first rule, which says that the data item being read should be read by the same transaction initially. So in this schedule, the transaction that is reading data item A initially is transaction T1. And now in our serial schedule also, the first transaction to read the data item A is transaction T1. So our first rule is satisfied. Now, before going to rule B, I'm going to go to rule C, which says that the final write should be done by the same transaction. So in this case, if you check in this schedule, here final write done to data item A is done by transaction T3. And even in this schedule, the final write done to data item A is done by transaction T3. And so rule C is also satisfied. Now we're going to move on to rule B. So for the rule B, we need to check the read and write operation order. So in this case, read is done by T1 and write is done by T2. So same order is maintained here also. And if you check any other order with read, then all read operations of T1 are done before the write operations of other transactions. So the read-write order is also maintained. And you can see in this case that this is a view serializable schedule. But if you check, it won't be a conflict serializable schedule. However, it is a view serializable schedule. So that's it for this video. I'll see you in the next one. Thank you for watching.